So our new unit is going to be looking at some things about chemical reactions. I'm still revisiting some properties about them that we have talked about before. But today I want to revisit some basics of making solutions and some of the vocab that came along with that, because it's going to be an intermediate step in several parts of things like FRQs, your ability to understand how molarity is connected to putting solutes and solvents and stuff like that. So, people at home, make sure you have your slides out for this lecture. And if you would go, please. So, the images, and really another great reason for you to have either already drawn or printed these out, is the images will show up a lot better in front of your face than they will up here, because this looks, it's not as easy to see. But what I want to just express is what actually happens when a solute is put into a solvent while building a solution. The separation, for example, if you look here, we've got this is a crystal of some kind. There's pluses and minuses. That's how I know it's a crystal. It's ionic. And then I can see water out here ready to attack. And if you look at what happens when a solution is built, it's actually based off polarity that helps water be the universal solvent. Polarity referring to the idea that water has both a positive and a negative region, but those regions can create this electromagnetic pull on different parts of the crystal that it's trying to dissolve. You can notice that what happens there is water is sneaking into the crystal to tear it apart and turn it into a solution. Dissolve it is a way to look at that. But the way that the water orients is something that I want you to really focus on. Like down here, if you look at the picture you have, that's an anion, all right? That's been pulled out of the crystal. But if you look at the way the water has oriented around the anion, it's the hydrogens that are actually pushing up against it. Well, why would the hydrogens be the part of the water pushing on the anion?
Because they're positive.
Because they're positive, all right? It's an electromagnetic orientation that water not only is getting in between and pulling apart that crystal, but it's orienting itself so that the pluses and minuses are near each other, all right? Because that's where the attraction is. You can see the opposite happening right here, all right? Look at your desk. You'll see that's a cation, and the water molecules are totally flipped. And oxygen's got his butt up against the cation because, of course, oxygen has that predicted negative charge. And that's the way that they're going to orient during this building of a solution. Yes?
Cation is positive. Right?
Correct, because there's a T in the word cation.
Okay.
Boom.
Jesus.
Got it. What did you say?
For Jesus.
What? No, not Jesus. He's in salt. Okay. I want to point out... I don't know. I just say things. I want to point out that this is not a bond where you see the water surrounding. There's no bonds there. All right. It's just an attraction that's showing you the way that those solutes actually become a part of the solution. So keep that in mind as we're talking about mixing things and adding that. This is the general process that's always going. All right, so let's revisit electrolytes. How many of y'all remember the light bulb experiments from last year? Those look like all Cummings kids. Anyways, if you weren't one of mine, then we took different solutions based on what type of electrolytes were dissolved in them and put it up against a light bulb probe, a probe connected to a light bulb, and we could see what the light bulb would do. Shine bright for a strong electrolyte, have dim brilliance for a weak electrolyte, or have no shine whatsoever for a non-electrolyte. But anyhow, if you remember, an electrolyte is a type of solute that promotes the movement of electricity through a solution. You can have strong. If it's a strong electrolyte, it will totally dissociate. Ooh, dissociate. What's that word mean? Separate. That's the separation of those ions, as what was happening in the previous picture. And then the weak electrolytes will not completely dissociate, and that's going to be really important for an exercise that we're going to be doing here in a moment. We can look at our light bulbs there. just to piggyback on the basic idea that I said, strong on the left, weak in the middle, non on the right. Now, in order for us to properly show dissociation the way that I want you to, I need you to be able to easily identify strong versus weak compounds. And what we're going to focus on here are the rules associated with acids and bases. So, somewhere in your notes right now, I need you to write down the phrase, I bring clay. Just off to the side, you can put it in quotes maybe. It's an acronym. I bring clay. Imagine you're going to a Play-Doh party. You know what you got to bring, right? Don't you shake your head at me. Clay.
Wait, can you please explain Jesus and salt joke? I can't
No. That's how we lose jobs. We have to edit that out. Okay.
Really?
Maybe. Now, the I bring clay is referring to iodine, bromine, and chlorine. Do you see them up there? Do you see the I bring clay hidden in those three acids? So we have hydroiodic, we have hydrobromic, we have hydrochloric. Now, those three acids you just memorize are strong. I bring clay, don't forget those. All right? Another way to tell that an acid is strong or not, though, is if, when looking at the formula, it's got 2 or more oxygens than hydrogens. For example, if we were to look at this acid, somebody yell out the name of it, get a gold star. Sulfuric acid, thank you. It would be hydrogen sulfate if it was gaseous, right? Because we don't use acid rules when the molecule's a gas. Anyway, this is sulfuric acid. Is sulfuric acid a strong acid or a weak acid? It's strong because there are 2 oxygens. Wow. There are 4 oxygens, 2 hydrogens. Therefore, there are 2 or more oxygens compared to hydrogens. Do you see it?
Yes.
Anytime that happens, it's automatically strong. So then what's an example of a weak acid? Well, what is the formula for nitrous acid? HNO what? No. NO2. That's nitrous acid, and that would automatically be a weak acid. All right, because it doesn't fall into I bring clay, and the hydrogen count is 1, the oxygen count is 2, so there are not 2 or more oxygens compared to hydrogens. Questions?
Yeah. What did you say about the first one?
I said exactly what that says right there, the second part. Any acid that has 2 or more oxygens than hydrogens. So that has 2 more, so you're good. So that's another very common way to tell weak from strong. Now, if carbon shows up in an acid, automatically weak. All right, carbon's a weak sauce, y'all. So, could somebody name an example of an acid that contains carbon?
Calcium carbonate.
That's not an acid. That's just a salt. Acetate. So what's the name of that acid?
Carbonic acid.
Okay, carbonic acid is usually the first one that's shouted out, but we went a different direction. So it's not acetate. If it's an acid, it would be acidic acid. All right. So acetic acid is HC2H3O2. All right, but do you see the carbon?
Yeah.
Automatically a weak acid. All right. Carbonic acid was shouted out a moment ago. All right, there's your carbonic acid. Contains carbon, automatically weak. Questions how I'm doing this? Y'all, this is to live in your brain. Memorize these rules. All right? Like forever. Now, what about bases? Well, there's first, second, and third.
I used to play baseball.
Baseball. Okay. 4 hydroxides. All right? Anytime hydroxide is bonded to an alkali metal, all right, it's going to be strong.
What was that?
All right, it's right there. Group 1 hydroxides.
Oh, okay.
Right there.
Favorite acid. Yeah,
Carbonic acid.
All right, so group 1 hydroxides are automatically strong. But there are some alkaline earth metals that are automatically strong also, and you just got to know barium, strontium, calcium. Ammonia, there at the bottom, is a common nitrogenous base that we talked about last year, especially when we were doing conjugates and stuff like that. But ammonia is a very common base, and it's automatically weak.
What about ammonium?
Ammonium is going to be an ion, so it's not falling into any of our categories here. It's going to be a part of a salt. I almost told my assault joke there, but I'll save it. Yes.
Oh god. Did you say that anything in front of the OH was strong?
No. It's got to be an alkali metal. All right, a group 1, or one of these 3 elements from group 2: barium, strontium, calcium.
So it's stronger, sir.
That would be make it strong. Yes, those items make it strong. Ammonia is a common weak base. So then what if we had this guy here, and I asked the question, will that compound dissociate at 100%? Will that compound dissociate at 100%?
No.
Why not?
Because it's not a squat.
Because it's weak. All right, that's a weak base. And 2 slides ago, or 1 slide ago, some slides ago, it says that strong acids and strong bases dissociate at 100%. Weak ones don't. All right, this is hydroxide bonded to beryllium, which is not an alkali metal and is not one of your group 2 exceptions. Therefore, it is a weak base. Barajas.
It's just one.
Yeah, so no one can laugh at it like that one video.
I'm talking to all of you back there. Okay. So, what are we going to do with this? I need you to be able to write what are called dissociation equations. It's real simple, but you need to understand whether or not you are dissociating, breaking apart, a strong sample or a weak sample. Because if it's a strong sample, you're going to use a normal yield sign, which just indicates that it's dissociating at 100%. If it's a weak sample, though, you're going to use what's called an equilibrium yield sign, which is simply a double-headed arrow to show that it's not dissociating at 100%. So let's take a look at what these look like. All right, so here we go. Somebody tell me the name of that acid. No, quit putting hydro in front of all of them.
Porous acid.
Perchloric acid.
Perchloric acid.
Be more impressive. Okay.
Yeah.
Are we okay with the way the yield sign is drawn on the screen?
Yes.
We are, because we draw a normal yield strong. Whoa, these checks got me all messed up.
Come on, Carol.
We draw a normal yield sign if it's strong. Look. How many oxygens?
4.
How many hydrogens?
1.
Strong acid.
Strong acid.
Strong, yes.
Strong
I don't know what's going on. What?
Could we say it's strong because it has the
That only works for those 3 specific acids, not containing chlorine. Y'all, the I bring clay was for those 3 acids only.
Okay.
Is it because there's
Iodine, chlorine,
That is
bro.
Is it because there's no oxygen?
Guys, the I bring clay is only these 3 guys.
It has an O.
Oh, the whole
All right, yes, the O makes it not that. That's hydrochloric acid, that's perchloric acid, 2 different acids. Okay.
So it's only strong because of the H.
Anyways, so it's going to completely dissociate. Hey, this is easy. You're just going to break it apart into its ions. We've got H plus and we've got ClO4 minus. It is now dissociated.
You don't have to put like H2.
No, not during dissociation. So that's a great question. She asked, but hydrogen's diatomic. Doesn't it need a 2? Not while it's sitting there with a charge.
So we're going to always make it
Yeah, while it's dissociated, yes. Because remember, while it's not dissociated, it's built a stable ionic compound. While it is dissociated, it's broken apart into its ions, which is what's making it electrolytic. It's that ion that is making it conduct electricity and have those characteristics.
So writing that 2 would make it
It would make it absolutely wrong. Now, before we go on to the next one, I want to point out that while this can happen spontaneously the way that we have it written, it could be added to water to force it to happen also. It would look a little bit different if we did that. So let's add perchloric acid to water and take a look at what happens. All right, still a strong arrow. All right, but this is going to get kind of Bronsted-Lowry. And if you remember, that's where protons were donated and accepted. Does anybody remember, do acids like to donate or accept protons? They like to get rid of them. What will this guy look like if you get rid of an H? ClO4 minus, because it's not just an H, it's an H plus. So look, it still creates that same ion. However, this next thing that it creates will be a little different, because where does that H go if this happens? So what happens if water gains an H plus? It becomes, yeah, what was it called? Yeah, ammonium. All right. Oh, no. Hydronium. Look at it. You got me all messed up. Knew it was an EM. That's hydronium. All right. So I'd like to point out that really either of these things are possible to be created during a dissociation of any of our acids here. It just depends on if water is going to be a constituent or not. But remember, both H plus and hydronium are characteristics of acids. Yes. Yeah, acids donate, bases receive. All right, and go. I mean, that's in your brain from last year. But yeah, you're definitely go. All right, next problem, please. All right, C6H12. What type of arrow should we add there?
Equilibrium. Yeah, they yield the equilibrium.
Now, while I've gotten y'all all wrapped up in strong versus weak, what's the third kind of electrolyte? A non-electrolyte, all right? Covalent compounds are non-electrolytes, all right? This compound, if put into water, will not dissociate. These two nonmetals bonded together, it's not an acid or a base, it's covalent, it's a molecule, it's a non-electrolyte. Therefore, there is no dissociation.
So the only ones that can be acids or bases are ionic?
The things that are going to dissociate are acids, bases, and ionic compounds. Yes, that's exactly right.
But like, can it be acid and ionic and base and ionic?
Well, acids do have an ionic attraction since hydrogen acts as a cation and anything it bonds to acts as an anion. So they are, like you said, kind of in the same boat. But we have to identify them separately because as we move into neutralization and stuff, it's going to matter if it's a acid or just a salt that's not acidic.
So hydrocarbons are never going to dissociate?
Correct. Hydrocarbons will never dissociate. Next one, please. What kind of yield sign should this guy have if he's going to dissociate? A normal one, because this is a strong base. Does everybody see how lithium hydroxide is strong? And then just break them apart. Lithium hydroxide. Because it's a hydroxide bonded to an alkali metal.
Oh.
Next problem. What kind of arrow? I know there's a blank there, I'll talk about it, but what kind of arrow do we need here? The equilibrium arrow. Because ammonia is automatically a weak base. Now, the reason there's a blank there is that ammonia only exists in gaseous form, so the only way to actually dissolve it in something is to add it to water. So, ammonia, put a star next to this because the AP wants you to just know that ammonia can only be created in a solution if it's added to water. These other examples can go with or without. Ammonia requires water.
Can you say that again?
Yeah.
Ammonia requires water to create a solution. Can't you just go home and watch the video? I'm just kidding. So we do have a Bronsted-Lowry situation here, and as we know, bases like to accept protons. All right, so for that NH3, if we're going to give him an H+, what will that make him? Yeah, ammonium, exactly. All right, and then what will water do if he gives away that H?
Hydroxide.
All right, so you can see how he's considered basic. He creates hydroxide.
So it's the one that has.
No, it's just that the bases always accept. So if the base is going to accept from water, the water had to give it.
So ammonia can only create a solution back with water.
Right. Yeah, he won't have one of these dissociations that he just is spontaneously dissociating. Is there another question on this slide? Okay, there is. So for ammonium chloride here, it's going to be a normal one because this is just a regular salt. However, you don't have that in your brain yet. Tomorrow, I'm going to be giving you the solubility rules. Remember, like nitrates are always soluble, and these guys are soluble unless they're bonded to these guys. That chart from last year. When you have that in front of you, you'll be able to easily see that this is an ionic compound that will 100% dissociate. And in this case, it would just be NH4 and Cl minus, nothing tricky. You try a couple. Go ahead and go to the next slide. I'd like you to solve both of these. Oh, you want? Yes, ma'am.
He thinks that he made an actual joke. Didn't we just do that? I don't believe.
No, I didn't. I just talked. But here, solve this. No, Jacob, solve.
He made a joke out of it himself. He's super proud of it.
No.
Add it to the comments on YouTube.
Oh, I will.
Give the mark that I tell the joke and then tell them how it's.
Oh no, yeah, I did.
I know. I saw it. Call me over if you need my help.
Excuse me?
We're going to get Aspen in play. Oh. And he's dead. Roosters can't fly, sweetie. What?
Okay. They can run really fast at the game, so.
All right, let's get some help. Let's go to cluster 3, seat 3. Hey, 3-3. What kind of yield sign did you use for the first one? Diego, it's totally you, dude.
Oh, no, it's one backwards and forward.
What's that called? Equilibrium. Don't help him. All right. Yeah, it's an equilibrium error. All right, and then Diego only. What did you say it dissociated into?
H plus C2H3 O2. That. Whoa.
Perfect. All right. Now, if you can't see acetate in there because you don't know your ions, then that's an issue. All right. But yeah, remember, it just breaks into its two parts, hydrogen and acetate. All right. Let's head over to cluster 4, seat 5. Hey, 4-5, what kind of arrow did you use for the second one? It is strong, all right? Because as you'll see when you have your rules in front of you tomorrow, all right, sodium chloride is a soluble salt, all right? And those are going to dissociate at 100%. All right, therefore, and what were the two things that you think it will dissociate into? Right? Perfect. Questions? Yes, ma'am.
There's like, oh, just
Other almost questions? All right, let's move on. So the other topic I want to cover today is what's created as we create our solutions, which is going to be molarity. Remember, molarity is going to look at the strength of the solution based on how much solute you've dissolved in that solvent. We've got our basic equation there. All right, if you remember, molarity is moles over liters. That's moles of solute over liters of solution, as the slide says. So that's an important equation to make sure you remember. It's on your equation sheet. I do want to point out that we've grown accustomed to using a capital M, molar, as the units for molarity. Totally cool. That's what I do. But the AP likes to use a different unit. They like to put moles per liters. Now that can actually be helpful because moles per liters tells you exactly how they got molarity. So I guess it's a good thing. But I've seen them used interchangeably. So I tried to make Schoology use them interchangeably. Molar, the capital M, and moles per liter are both acceptable units for molarity.
Oh my God, why didn't anyone tell me who needed?
All right, so we're going to do 1 and 3 together. Well, I'm going to have you do 3 by yourself, but we're going to skip that middle one. So to use this equation in the most basic way, all right, it says calculate the molarity. So we want to calculate the molarity. It gives you a mole count of 0.875. It gives you a liter count of dose. So to find molarity, you would divide. Can anybody shout out an answer?
0.43.
Oh, that was too many numbers.
Yeah, sorry. 0.44.
Oh, it's still too many numbers.
0.4.
0.4, right.
Nice.
The answer here can only be 0.4 moles per liter because we can only have one sig fig, so be careful. Questions on how I did that? Solve the third one by yourself, please. Do number 3.
Would we have to convert it to liters?
Let's go talk to person 4, 6. That will be Aspen. Hey Aspen, what did you just have an answer?
Yeah, I know it.
What did you get?
I got 0.1 moles.
Y'all agree or disagree?
Disagree.
I disagree too. So, here's the issue, guys. The milliliters cannot go into this equation, all right? So it gave you 100 milliliters. Remember, to turn that into liters, you divide by 1,000, all right? In other words, you slide the decimal to the left that many times. So really, the work becomes molarity equals your mole count of 0.875 divided by 0.1. What's the correct answer? 9. 9 molar
Did number 2 in there?
is, oh.
Yeah.
The correct answer is 9 molar. Questions? Guys, if you have conversion issues, you've got to come see me. I can straighten you out because you've got to be able to easily convert those types of things. Okay.
So we're not doing 2?
What?
We're not doing 2?
No, we're not doing numbers. We don't have time. I'm going to run out of time anyways. Now, I want you to underline the word volumetric in the notes that you wrote before you got here. And because it's a good word to have on your head when you're doing some of the FRQs on AP. Volumetrics are superior to graduated cylinders. Usually if you run into a FRQ question that wants you to describe how you're going to do some part of an experiment or something, y'all's brain when you're measuring something goes to graduated cylinders because that's what you've used up through this point. The reason I want you to try to remember the word volumetric is because they're not graduated. A volumetric is a piece of equipment designed to hold only one volume of a solution. It's got one line on it. All right, you have a 500 mil volumetric. You have a 200 mil volumetric. So instead of having all those graduations and hitting a line, there's one line to hit because that's the only thing that it measures. So if you can use volumetric when describing how you're going to create a solution instead of graduated cylinder, readers, the graders, will they'll be nicer to you for the rest of their grading. They like your brain at that point.
Wait, so it's like an exact, like 7.2,
Then you'd have to go graduated. Yeah. So, but most experiments don't actually call for a hundredths of a place, a weird number. It'll be a whole round number. All right. So we're going to end with some basic calculations. Try to get it into your brain how we do some of this molarity. I don't think I meant to erase the equation. So let's figure these out together. Stop me if I do something you don't understand. We've got some given information here. Hey, look, it gives me a molarity. Do you see the molarity?
Yes.
0.05. It gives me 0.05 with a couple other sig figs molar. All right? And it also, what's that other number? What else does it give you?
5 million.
Gives you a volume. All right? It gives you milliliters. Ooh, I don't like milliliters, though. How do I turn milliliters to liters? Divide by 1,000, slide the decimal to the left 3 times, you're going to end up with 0.5. All right? And this is now in liters, which is good. Now, this wants to know how you would make this. Now, it turns out that in the lab, you don't have a device that measures moles, but you do have devices that measure what more common unit? Grams, all right? So we did this in pre-AP. We don't want the moles that this is capable of giving us. We can find the moles, though, because we can easily convert moles to grams, right? So let's find moles. All right, now some of y'all have always thought it's easier to put a whole number over 1 and cross multiply. I don't care how you do your algebra, but I don't mind teaching it like that. Bless you.
Thank you.
That was Gilbert. Anyway, so this way we're just going to get our mole count, and then what is the product of the other cross? 0.025, right? Now, again, if we had a device that counted moles, then we could say, okay, well, you'd go back to the lab and you'd find this many moles. But I don't have anything to do that. So we want him in grams. So let's take a look at how we would do that. Not like that. What a treat for the people at home. Okay. So we could take my mole count of 0.025, and we just want to turn that into grams. All right, we want our diagonals to match. Our conversion factor is 1 mole equals periodic table grams. And now I need your help, because where on the periodic table do we need to go look? Copper 2 nitrate is, I'm sure, what you wanted to say, so you're not sounding like letter animals out there. Cu parenthesis NO3. Say what it is, guys. Copper 2 nitrate. Somebody find me that number.
I love you, John. John Anthony Garza Jr.
Oh, that John.
Yeah, that John.
That's terrible.
I have a number, but I want someone to shout at me. That's what I got. I got 187.57, which of course is the molar mass, so it's copper plus 2 nitrogens plus 6 oxygens. Now, solving the grid, will give you the amount of grams to make this happen. And I think it's going to be 4.69. Now, look at the way the question is worded, though. It says, how would you prepare? This doesn't want you just to give it a number. It wants you to say how you would prepare. Now, before you write, listen. Here's what I think is the perfect answer on the AP exam. I would get a 500 mil volumetric. I would add 4.69 grams of copper 2 nitrate to the 500 mil volumetric. I would then pour water on top of it up to the line. Now look here, still don't write. If you do it the other way, or if you were to say something like, I would add 4.69 grams of solute and then pour in 500 mils of water, that's wrong. Because if you already have this many grams in there, it's taking up some volume. Not a lot, but it's taking up some volume. If you pour 500 mils of water on top of that, it's going to go over the line. Maybe not by a lot, but you have the wrong amount if you do it that way. So it's important to dictate that you're going to add the sample, and then you can say, and then fill it up to the line. Because if you've already said you're using a volumetric, you don't have to be specific on what line. There's only one line. All right? And then you might even be really smart and say, then I put a stopper in it and invert it. All right? Ooh, now you're really telling them how you would make the solution. But the order by which I explained it would be vital to getting the answer right. Or 100% right, because there's partial credit all over the thing. Does that make sense? I'm running out of time. Show them the next problem, and we'll get through it. Hey, the next problem uses a different equation. If you look at the way that it reads, you'll notice that it wants you to dilute a solution. Does anybody remember the dilutions equation?
Oh, no. I thought you were going to ask what that means.
I know what it is.
All right, it's M1V1 equals M2V2. All right, and this is where you can take a more dangerous solution. This is the equation I use most often on the Madison campus. All right, I do this a lot to get your labs ready. But where I take the stronger solutions that are like 18 molar that are going to kill you and turn it into 2 molar so that you just hurt a little bit. All right, but here's how you solve. These problems are straightforward. This is where it'll talk about a solution like, look, it says 250 mils. All right, that's a volume, 250 mils of a 0.04 molar, that's a molarity, 0.04 molar solution. And it wants to know what volume you would need, all right? So it's looking for a volume that you would need if the molarity was going to be 0.5. You can trace the way the question's written to how those all connect to each other. And then solving for x is super straightforward. Got 2 whole minutes for us to solve for x. But 0.04 times 250, I think, is 10, maybe? Did you get 10 there?
Yes.
And then 0.5 times x is... Ooh, y'all got that one fast. I take credit. Isolate the x. And then what volume would you need for it to be, well, originally, it's kind of swapped, but to be originally at a strength of 0.5? 20, but with a decimal, all right? Make sure your sig figs are right. It would be 20 with a decimal.
Why do we have to include the decimal?
Because if you look at all your starting numbers, 3 sig figs, 2 sig figs, 3 sig figs. My answer will have 2 sig figs.
Oh, okay. I'm looking at 10.
Yeah. Sorry.
Mr. Cummings.
My bad.
Mine.
The first assignment on Schoology is good to go. I just didn't write it yet. I'm sorry, but more tomorrow.